Good morning, all. Today we are going to be talking about calculating energy in electric fields and using that calculated energy in order to solve problems in change of energy and things like that. So let's go ahead and get started. So I wanted to return to the electric potential in an electric field. Because previously I've described going up in an electric field as increasing potential. But up is relative and refers to moving against the direction of the electric field. So if you're moving against the direction of the electric field, you are gaining electric potential. So in this case, that would be moving to the left is moving up the electric field and therefore gaining electric potential. And if you're a positive object, this means that you're gaining electric potential energy. Down is, of course, also relative because that's moving in the same direction as the electric field, and you're now losing electric potential. So if you're a positive object, you're going to be losing electric potential energy. If you're a negative object, you're going to be gaining it. And just like going side to side in a gravitational field doesn't gain gravitational potential or gravitational potential energy, moving side to side in an electric field doesn't do anything. So in this case, it's that moving up and down in an electric field that doesn't end up mattering. Or up and down in this one that doesn't end up mattering because the electric field is left and right. And as we can see, as I spin this around, it doesn't really matter which direction it's going. It's the relative to the electric field that ends up mattering. So let's do an example problem with this. So proton therapy clinics are absolutely amazing applications of particle physics. So protons are accelerated to about a third of the speed of light and then steered using magnets into a tumor in order to help kill it. And this form of radiation is a lot more precise because you can aim in 3 dimensions. So you can aim for depth too. And that's something that you can't do in traditional radiation treatments that involve gamma rays or electrons. Those are a lot cheaper though. So what kind of electric potential difference does a proton need to experience in order to get up to this kind of speed? So like I said, these are really cool, and if anything were to steal me away from teaching, it would be medical physics. Not just because the treatment centers look like they're straight out of Star Trek, but also this is a picture of one of those accelerators. And so each one of those chambers has a truly massive amount of voltage, massive amount of electric potential in order to get the protons up to relativistic speeds. Now, for the purposes of this problem, we're going to ignore relativity. So we're going to end up with an answer that's a little bit smaller, but it'll make the math a heck of a lot easier. So let's do this for ignoring special relativity. So we need to know the charge of a proton, and that's the fundamental charge. So fundamental charge, you might remember from chemistry, is 1.6 times 10 to the negative 19 coulombs. We also need to know the mass of the proton. So I looked that up, and the mass of the proton is 1.67 times 10 to the minus 27 kilograms. And then we also need to know the speed of light, or c. So that's 3 times 10 to the 8th meters per second. So what we have here is basically your standard conservation of energy. So we're going from electrical energy to kinetic energy. So we split that apart. So kinetic energy is, of course, 1/2 mv squared. The electric energy that we're looking for here is going to be the voltage, that electric potential, times the charge. And we're going to be looking at that change in electric potential, that change in voltage. So we're going to solve for V. I got that in here. And you notice the way that I ended up grouping these variables over here is 1/2 times the mass of the electron over the charge, or rather mass of the proton over the charge of the proton. So I've expressed this in terms of its mass-charge ratio, which is something that you do a lot in these sort of problems, because it's that ratio between mass and charge that matters. And that's where we're going to be ending up getting this necessary change in potential from. So, put some numbers in here. Mass of the proton, that's the 1.6 times 7 times 10 to the negative 27 kilograms. That fundamental charge, 1.6 times 10 to the minus 19 coulombs. And then a third of the speed of light. So 1/3 times 3 times 10 to the 8th meters per second. The 3's are, of course, going to cancel. So put this into the calculator, and what we end up with is 52 megavolts. So that's 52 million volts, or 5.2 times 10 to the 7 volts, which is a really big number. The reason why you ended up with all of these big copper containers on the previous page is because that 57 megavolts is too big to go in one step. So each one of these containers, you can see the lighter copper strips. Each one of those, it has a certain, granted very large, a potential difference going across it, and that's stepping the potential up one step at a time. So that is going to accelerate the proton along this LINAC, or linear accelerator. So you should have all the information that you need to know in order to solve your next problem set, and I hope you have the most wonderful of days.